Welcome to our quantum deep dive.
Today, we are diving headfirst into the quantum world to look at one of the universe's most fundamental mysteries, antimatter.
And our guide for this journey is a really fantastic essay by York O.A. Schnippet. We're going to be zeroing in on a real heavyweight, a particle that's as strange as it is important, the anti-bottom-quark.
So let me ask you something kind of wild. Just imagine, for a second, that every single particle that makes you, had a secret, identical twin. But this twin is its perfect opposite, an evil twin, if you will, just waiting to meet. And when they do, both of them vanish in a brilliant flash of pure energy. Well, that's not some sci-fi plot. That's the actual real-world science of antimatter.
And to really get our heads around this, here's the game plan. First, we're going to explore this idea of a mirror universe to understand what antimatter even is. Then, we'll zoom right in on our main event, the heavyweight particle. After that, things get exciting. We're going to play detective and see how scientists chase this thing down. And that chase, well, it leads us to solving a huge cosmic crime. And finally, we'll have some fun and look at the wild sci-fi future this research could unlock.
Right, so before we can go hunting for something as specific as an anti-bottom-quark, we really have to set the stage. We need to get comfortable with the whole concept of antimatter itself. Think of it as the universe's perfect, and I mean perfectly destructive reflection.
Okay, so how does this mirror thing actually work? It's actually pretty straightforward. You know the electron, right? It's a key part of basically everything. Well, its antimatter twin is called a positron. And here's the deal. It has the exact same mass as an electron, but its electric charge is the perfect opposite, positive one instead of negative one, and when these two meet, it's game over. They don't just bump into each other, they annihilate. Their entire mass gets converted into a burst of pure energy, just like Einstein's famous E=mc² formula said it would.
Now, the stuff that makes up protons and neutrons and atoms, that's built from even smaller particles called quarks. And quarks come in 6 different types, or flavors, which is a fun way to think about it. You've got the classics, the up and down quarks. They make up most of the everyday matter around us. Then you have the more exotic, strange ones. Literally, they're called charm and strange. And then at the top of the list, you have the true heavyweights, the top and bottom quarks. And, you guessed it, for every single one of these, there's an antiquark just waiting in the wings.
All right, so let's focus in on one of those heavyweights. We're talking about the bottom quark. This thing is a true giant in the subatomic world, and its mirror twin, the anti-bottom quark, is exactly what we're here to talk about. This is our star player.
This table just lays it all out so clearly. Look at this. The mass and the spin, they're identical. No difference at all between the quark and its antiparticle. But check out the other properties. They're perfectly flipped. The electric charge goes from a negative 1/3 to a positive 1/3. And then there's this other wild property called color charge. Now this has nothing to do with actual colors we can see. It's a type of charge related to the strong nuclear force that holds everything together. And just like the electric charge, it's also perfectly inverted. So if one is, say, blue, its counterpart is anti-blue. It's a true mirror image.
So what happens when this heavyweight particle and its antimatter twin actually cross paths? Well, sometimes, for just a fleeting moment before they annihilate, they can form this incredibly unstable mashup called bottomonium. Just picture it, a bottom quark and an anti-bottom quark caught in this intense, frantic orbit around each other. It's like a doomed dance, a tiny, super heavy, makeshift atom that's guaranteed to end in a massive burst of energy.
Okay, so if these particles are so ridiculously unstable, if they just pop into existence and then vanish, how in the world do we study them? Well, this is where the whole thing becomes a high-tech detective story. We're literally chasing a suspect that exists for a fraction of a moment in time.
Yeah, get this, 1.5 trillionths of a second. That's about how long an anti-bottom quark even exists before it decays into something else. I mean, you can't even process that. It's gone almost as soon as it's made inside a particle accelerator like the Large Hadron Collider at CERN. So you can't see it directly. You can't catch it. It means you have to stop looking for the particle itself and start looking for the clues it leaves behind.
Okay, let's walk through this high-speed chase. Step 1. Scientists smash protons together at just shy of the speed of light. Step 2. The raw energy from that collision creates a pair of particles, our bottom quark and its anti-bottom twin. Step 3. The anti-bottom quark is super unstable, so it immediately grabs some nearby quarks and forms a new particle called a b-hadron. Now here's the key. Step 4. This b-hadron actually travels a tiny distance, just a few millimeters, before it decays, and that is the fingerprint.
Scientists aren't looking for the quark. They're looking for this secondary vertex, a decay point that's just slightly off from where the main collision happened. It's the smoking gun that proves an anti-bottom quark was there.
Now, you might be thinking, okay, that's a lot of work just to find the ghost of a particle that vanished in a trillionth of a second. And you'd be right. So why do it? Because that little particle and the clues it leaves behind might just hold the answer to one of the biggest, most fundamental questions in all of science, the mystery of why we exist at all.
And here is that mystery, the great paradox. All of our best theories tell us that the Big Bang should have produced perfectly equal amounts of matter and antimatter. But if that happened, every particle should have found its antiparticle twin, and the entire universe should have annihilated itself, leaving behind nothing but a sea of light. And yet, here we are. The Earth is here, the stars are here, you are here. So where did all the antimatter go? Why did matter win?
Well, the prime suspect in this cosmic crime scene is a phenomenon with a very cool name, CP violation. Now, C stands for charge, and P stands for parity, which is basically a fancy way of saying looking in a mirror. For a long time, physicists assumed the universe was perfectly symmetrical, that an antiparticle would behave exactly like a mirror image of its matter twin. But it turns out that's not quite true. The mirror is flawed. There's a tiny crack in it. We've discovered that some particles and their anti-twins decay at slightly different rates.
And this right here is where our anti-bottom quark becomes the hero of the story. It turns out the particles where we see this asymmetry, this CP violation, most clearly are a type of B hadron called B mesons. And what are they made of? Bottom quarks, or they're antiparticles. So by studying them with incredible precision, we can actually measure that tiny imbalance. It's kind of like studying a tiny wobble in a spinning top to figure out the forces acting on it. And that little wobble in the laws of physics might just be the reason a tiny sliver of matter was left over after the Big Bang, just enough to build everything we see.
Whew, okay, so we've gone from the tiniest particles imaginable all the way back to the birth of the universe. Now, let's totally switch gears and look forward. Let's put on our futurist hats and ask, what could understanding these bizarre particles actually lead to? What kind of visionary technology are we talking about?
So one really far-out idea is in quantum computing. You know that doomed dance we talked about, bottomonium? Well, it has very distinct energy levels. Could those energy states one day be used as the 0 and 1 of a quantum bit, a qubit? Now this is a huge leap for sure. Their incredible instability is a massive roadblock. But it's the kind of thinking that pushes us to imagine encoding information in the most fundamental pieces of reality itself.
A vision that feels a little closer to home is using these things as ultra-precise sensors. Because these quark-antiquark systems are so exquisitely sensitive to the forces around them, they could, in theory, act as perfect little probes for environments we could never ever hope to visit. Imagine being able to measure the conditions deep inside the core of a neutron star. They would be like our subatomic canaries in a cosmic coal mine.
And of course, we have to talk about the big one, the one straight out of science fiction, antimatter propulsion. The reason this is the holy grail of space travel is because matter-antimatter annihilation is by far the most efficient energy source possible. It converts 100% of a particle's mass directly into energy. Now, are we close to creating and storing enough anti-bottom quarks to power a starship? No, not even a little bit. But the fundamental physics, it's completely sound.
So, let's bring it all home. We've seen that anti-bottom quarks are so much more than just some obscure particle on a chart. And as Jörg Schneppat's work really highlights, they're a critical tool, they're a window. They let us test the deepest symmetries of our universe, they help us hunt for new physics that we don't even know exist yet, and yeah, they push us to dream up technologies that are still way out on the edge of what's possible.
And that's our deep dive into the incredible world of the anti-bottom quark, all inspired by the work and the essay of Jörg Schneppat.
It's fascinating stuff. To learn more, you can check out the website schneppat.de. Thanks so much for joining us for this explainer.
Schneppat.de is a private project by Jörg Schneppat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.